It's 9 a.m. Black Friday begins. 50,000 customers open your checkout within seconds. Database CPU hits 100%. Response time explodes from 40 milliseconds to 12 seconds, and orders begin failing. But here's the strange part. Every request is asking for almost the same data. Engineers inspect the logs. They expect expensive database queries. Instead, they discover something surprising. Thousands of users are repeatedly requesting the same product details, prices, and inventory. The database isn't overloaded by complexity, it's overloaded by repetition. So why isn't the application remembering yesterday's answer? The real bottleneck isn't computing the answer. It's fetching the same answer from disk again and again. Reading from RAM takes microseconds. Reading from disk is thousands of times slower. What if the application could keep frequently used data in memory instead of asking PostgreSQL every single time? This is exactly the problem Redis was built to solve. Redis stores frequently accessed data directly in memory. Before touching the database, the application first checks Redis. If the answer already exists, the request finishes almost instantly. But what happens when Redis doesn't have the data? Let's follow a real request. A customer opens the product page. The API first asks Redis for product 101. Redis immediately finds the value in memory and returns it. The database is never contacted. This is called a cache hit, and it's the reason Redis can remove millions of unnecessary database queries every day. Now imagine another customer requests a product that's never been cached before. Redis checks its memory and finds nothing. This time the API must query PostgreSQL. After receiving the result, it immediately stores a copy inside Redis before sending the response back. The next customer will become a cache hit. This strategy is called cache-aside. But where exactly does Redis keep this information? Unlike PostgreSQL, Redis doesn't fetch rows from disk for every request. It keeps the entire value directly in RAM. A lookup becomes a simple key search inside memory. That's why Redis can respond in less than 1 millisecond. But if everything stays in memory forever, won't RAM eventually run out? Redis solves this with expiration times called TTL, or time to live. Every cached value can carry a countdown timer. When the timer reaches 0, Redis automatically removes that key and frees the memory. Fresh requests simply recreate the value when needed. But deleting data too aggressively creates another production problem that catches many engineers by surprise. Everything looks perfect until thousands of cache entries expire at exactly the same moment. Suddenly, every request misses Redis and rushes to PostgreSQL together. Engineers call this a cache stampede. Instead of protecting the database, Redis accidentally sends an entire traffic wave directly into it. So how do companies like Amazon and Netflix prevent this disaster? Production systems solve this by allowing only one request to rebuild the cache. That request becomes the leader. Every other request briefly waits for the new value instead of querying PostgreSQL. Once Redis is updated, everyone receives the same cached response. The database processes one query instead of 10,000. But Redis still has another secret behind its incredible speed. At this point, you might wonder, if Redis serves millions of requests every second, where are all the worker threads? Surprisingly, Redis processes commands using a single event loop. Instead of hundreds of threads competing for locks, it rapidly switches between thousands of network connections, keeping the CPU busy without wasting time on synchronization. Imagine a receptionist answering thousands of visitors. Instead of hiring thousands of receptionists, one expert quickly serves whoever is ready while others wait their turn. Redis works the same way. It never blocks waiting for slow network operations. It immediately moves to the next ready request. But if Redis uses only one CPU core, can it still scale across an entire data center? One Redis server is incredibly fast, but eventually every machine reaches its limit. Instead of building a bigger server forever, Redis scales horizontally by splitting data across multiple nodes. Product data might live on one node, user sessions on another, and shopping carts on a third. But once data is spread across many servers, how does Redis know where every key belongs? Redis cluster solves this using hash slots. Every key is hashed into one of 16,384 slots. Each Redis node owns a range of slots. When the application calculates the hash, it immediately knows which server stores the data. There's no searching and no broadcasting requests. But another question remains. What happens if one Redis server suddenly crashes? If a Redis server suddenly fails, applications can't simply lose all their cached data. Redis protects against this using replication. One primary node continuously copies every change to one or more replica nodes. If the primary crashes, a replica is automatically promoted to become the new primary, allowing applications to continue with minimal interruption. But how does Redis detect failures fast enough? This responsibility belongs to Redis Sentinel. Sentinel continuously monitors every Redis server by sending heartbeat messages. If the primary becomes unreachable, multiple Sentinel instances vote to confirm the failure. One replica is promoted, clients receive the updated address, and traffic resumes automatically. But Redis isn't only a cache. It can do far more than storing temporary data. Many engineers think Redis is just a giant dictionary. In reality, Redis provides specialized data structures optimized for different problems. Strings store cached objects. Lists power activity feeds. Sets remove duplicates instantly. Sorted sets rank players on leaderboards. Hashes efficiently store objects. Choosing the right structure often makes the difference between an average system and one that scales effortlessly. This is why Redis appears almost everywhere. E-commerce websites cache product information. Social media platforms build timelines. Gaming companies maintain live leaderboards. Authentication services store user sessions. Rate limiters stop API abuse. Message queues coordinate background jobs. Even AI applications use Redis to cache expensive model responses. Suddenly, Redis isn't one feature, it's infrastructure used across almost every modern application. Let's put everything together. Applications first check Redis before touching the database. Cache hits return instantly from memory. Cache misses fetch from PostgreSQL and populate Redis for future requests. TTL keeps memory under control. Replication and Sentinel provide high availability. Clustering scales across servers. And specialized data structures solve problems far beyond caching. That's why Redis has become one of the most important technologies in modern backend engineering.